This little extra section is going to talk about function behavior of implicitly defined functions. So far, all the curves we've analyzed have been functions. We could identify critical values using the first derivative and evaluate the function to get the corresponding output. But what about other relations that aren't necessarily functions? So we want to be able to look at those too. This first example is an example of that, right? It's not a function. It doesn't pass the vertical line test. It's the graph of x squared over 4 minus y squared equals 1. But we can look at this graph. We can also look at the function of this graph, but where does this graph appear to have vertical tangents, and where does this graph appear to have horizontal tangents? Well, it has vertical tangents here at x equals -2 and x equals +2. Being that it's a hyperbola, it has no horizontal tangents. Number 2, in which quadrants is this curve increasing, and in which quadrants is this curve decreasing? Well, we can see that it's increasing here. It has a positive slope in the first quadrant, and it also has a positive slope there in the third quadrant. And likewise, we can see that it's decreasing in the second and in the fourth quadrants. Now let's see if we can apply what we've learned about the first and the second derivative of functions to a relation that's defined implicitly. So pause the video, please, and try to find the first derivative. You're going to have to use implicit differentiation. The first step, there's no product rule or quotient rule or even chain rule. We're just finding the first derivative, so that's what we get in our first step. Now remember, we're finding dy dx, so we actually need to solve this equation now for that y prime. Adding the 2y y prime over, and then simplifying, I get 1/2 x equals 2y y prime. And now I just need to divide by 2y. Now I get that y prime equals x over 4y. So how does this equation for dy dx support our answers for questions 1 and 2? To determine how my first derivative supports my answer for question number 1, remember, question number 1 is asking, when does this graph have vertical tangents and when does it have horizontal tangents? Remember, those tangents are going to occur when my first derivative is either equal to 0 or undefined. So my derivative is going to be equal to 0 when x equals 0. But if we come back up here and look at my original equation, if I let x equal 0, this whole first term becomes 0. And when I try to solve what's remaining there to find out what my y coordinate would be, I get that y squared equals -1, which we know we can't do. So x equals 0 is actually not going to be a critical point. But now let's look at when my first derivative is undefined. My first derivative will be undefined when y equals 0. And when we plug y equals 0 into our original equation, and we solve that for x, we get that x equals plus or minus 2, which is what we got for our vertical tangents in problem number 1. Now let's take a look at how this supports question number 2, in which quadrants is the curve increasing and which quadrants are the curve decreasing. Well, let's just think about this. Y prime is going to be positive if both x and y are positive, or if both x and y are negative. And where does that occur? Where are both x and y positive is in quadrant 1, so it would be increasing. And where else is x and y positive is in quadrant 3, where it's also increasing. So when is the curve decreasing is when x and y are opposite signs. So again, that's going to occur in quadrants 2 and 4. So far everything we've learned about the first derivative and what it tells us about our function or relation, curve, whatever you want to call it, is still holding true. Now let's look at when is the curve up above concave down and when is it concave up. So it's concave down in the first and second quadrants, and it's concave up in the third and fourth quadrants. How can that relate then to the second derivative? They're giving us the second derivative, -4 over 16y cubed. How does this equation, the second derivative, support our answer about our concavity in example number 5? Well, if you think about it, in quadrants 1 and 2, my y is positive, which would make my overall second derivative negative. And remember, when your second derivative is negative, it is going to be concave down, which is what we determined in question number 5. And then also, when y is negative, quadrants 3 and 4, right, it's below the x-axis, so my y-coordinate would be negative. And I cube a negative number, I'm going to get a negative. So then my negative over my negative gives me my second derivative is positive, which means it's going to be concave up in the third and fourth quadrants. So what are the important ideas about behaviors of implicit relations? There's really not anything new here. First of all, implicit differentiation can be used to find the first and second derivatives of any relation or function. Critical values still are going to be the points where the first derivative either equals 0 or is undefined. The only difference in this point is that you are going to have to possibly find x values and y values. Again, don't forget that you have to make sure that they satisfy the original equation and you don't get an undefined relation. And then finally, the curve is increasing when the first derivative is greater than 0 and decreasing when the first derivative is less than 0. And it's concave up when the second derivative is greater than 0 and concave down when the second derivative is less than 0. And again, make sure you are specifying both x and y values. So let's do some problems. Consider the curve in the xy plane given by that function x squared minus y squared over 5 equals 1. It is known that the first derivative is 5x over y and the second derivative is negative 25 over y cubed. I actually would like to challenge you to find and get that second derivative. It's a tricky one. If you can get that second derivative that they give you from that function, you rock. So let's just take what they've given us at face value and let's move on with that. Find the critical points of this curve and justify your answer. So again, remember the critical points occur when the first derivative is either equal to 0 or undefined. So let's start out looking at when this function is equal to 0. And it's going to be equal to 0 when x equals 0. However, again, make sure that you're plugging it into the original equation. If I plug 0 in for my x, and I try to solve this for y, I'm going to end up with y squared equals negative 5. And again, like that problem we had on the first page, that's undefined. We can't take the square root of a negative number. So x equals 0 is not a critical number, but now let's determine where this function is undefined, and it's going to be undefined when y equals 0. When y equals 0, and I plug that 0 back up into my equation, I get x squared equals 1, and so that I get my critical values are plus or minus 1. My critical values then, critical numbers I should say, critical numbers are 1, 0, and negative 1, 0. Those are going to be our critical points. I want to clarify that I have misspoken a couple times. Critical values is a term that is used in statistics. In calculus, we should be talking about critical numbers and critical points. 1, 0 and negative 1, 0 are critical points because I actually have an xy ordered pair. I can actually pinpoint that number. All right, is the curve increasing or decreasing in quadrant 4? How do we determine that? Let's think about what's going on in quadrant 4. In quadrant 4, we know that my x value is positive and my y value is going to be negative. And when we're talking about increasing or decreasing, we're thinking about our first derivative. In this case, we're looking at 5x over y. So in our fourth quadrant, if my x is positive and my y is negative, then my first derivative is going to be negative, which means that my curve is decreasing. Similarly, for question number C, is the curve concave up or concave down? And again, we're looking in quadrant 4, so my x is greater than 0 and my y is less than 0. And if I look at my second derivative, which is negative 25 over y cubed, if my y coordinate is negative and I cube it, I'm going to get a negative, which means my second derivative is going to be positive, which means that in quadrant 4, my curve is concave up. Question number 2 is just asking us to find the derivative. So this is just kind of going back to that previous chapter. I think it was chapter 3. You're just using implicit differentiation. And remember, in that first term, you're going to have to use the product rule, and then you are going to have to use the quotient rule, and then you are going to need to solve for your y prime. So that's what we get in our first step. Then I'm just going to kind of simplify things, pull everything together. So in that step, I just kind of cleaned things up, and I took my fraction to the other side. And now I don't particularly like fractions, so I'm going to multiply both sides by y squared to get rid of that fraction. Now I don't have any more fractions, but now I need to get all my y primes on one side and everything without a y prime on the other side so that I can factor it out and solve for y prime. Again, bringing all the y primes to the left and everything without a y prime to the right. Now on the left, I'm going to factor out my y prime. And now in my last step, I just need to divide to get my y prime by itself. So solving it the way I solved it, you would have gotten that answer. Back here in this step, one of these steps, if you would have brought things to the opposite sides than I did, you could have gotten this answer. Those are identical answers. It's just a matter of if you factor a negative out of the top and bottom of both of these, the -1 and the -1 would cancel, and you would end up with that equation. But just so you know that you could end up with two expressions that look kind of similar, but also look kind of different. So you can just double check to see that they would be equivalent. And question number 3. Which of the following describes the y-coordinate of the points on the curve e to the x equals sine of y, where the curve has a vertical tangent line? Well, it's looking for a tangent line, so we need to, first of all, find the first derivative. So go ahead and pause the video and find the first derivative, and then see if you can find out where that first derivative is equal to 0. So there's the first step in taking the first derivative. Don't forget that you're differentiating implicitly, so when you do the y, you need to have that y prime. Now solving this for y prime, I get e to the x over the cosine of y. E to the x is always going to be a number, so this fraction will never be equal to 0, but we need to determine where it's undefined. So where is the cosine of y equal to 0? The cosine is equal to 0 at pi over 2, 3 pi over 2, right? Every odd pi over 2. So if we look at these, we have a pi over 2, but pi over 2 plus 2 pi n would take us all the way around the circle. So since it's not giving us an option of 3 pi over 2 with either of those, we're going to disregard that. Now we need to determine whether it's pi over 2 plus n pi for all integers or all non-negative integers. This isn't limited at all, so remember we could go backwards on the unit circle or on the coordinate plane. So it doesn't necessarily have to be all non-negative integers. So the third answer would be your correct answer. If you have any questions on this, I hope to see you in class. And again, I really challenge you to go back and find the first derivative and second derivative of example number 1 and see if you come up with their second derivative.